to our viewing audience, welcome. Okay, I want to start chapter 7 today. As you can tell, chapter 7, the test for chapter 7 will be Monday, March the 3rd. I'm trying to put as many tests on Monday and Tuesday as I can, so you'll have the weekend to work on. Chapter 7 is interesting. Let me tell you just a minute about chapter 7. Our objective today is to revise and develop strategies for handling transcendental functions in limits. What's a transcendental function? Years ago, I asked that to a class. I said, what's a transcendental function? And they said, that's a hard one. They said, that's what transcendental functions are. They're hard. Transcendental functions are things like exponentials, logarithms, hyperbolics, trig functions. You guys surprised me on that first test. I gave you some pretty easy transcendental functions, and some of you act like you're terrified of logs and exponentials. And I'm going to use this chapter to try to erase that. Have you ever noticed your textbook? Your textbook says calculus, and then it says early transcendentals. What early transcendentals means is that most of you had either Ms. Hardy or myself, and know that we start teaching exponentials, logs, and trigonometric functions. We start teaching derivatives of those at the same time we teach other derivatives. And we've already used them in Cal 2, and you know how to integrate sine, cosine, tangent, e to the x, and so on. What that means is, as we teach a concept, we teach transcendental functions. Used to, in calculus textbooks, chapter 7, this very chapter, was where you first saw transcendental functions. It's where you learned how to take derivatives, how to take integrals, and to do everything with them. Why this section is in our book, I'm not sure, but I'm going to use it to do a little bit of review of transcendental functions. I didn't like what I saw in that first test, and I'm going to try to help you a little bit and make you feel a little bit more comfortable. You cannot avoid logarithms, exponents, and trig functions if you want to be engineers, and I happen to have one in the room, dearly love exponential functions. True? Why? Because we Americans like the biggest and the best. And an exponential function is something that models the biggest, the fastest. And you engineers are going to want to know how to maximize things, how to make things go as fast as they can, as soon as they can, or how to cool something down as quick as you can, or how to get it hot as quick as you can. And those are often modeled by transcendental functions. So I'm telling you, learn to love them, because you don't have a choice. Okay? All right. And this chapter now is a review for you in many ways, but it's a timely review. So here's my sort of review. Any calculus student likes to take the derivative of e to the x. Would you agree? And I personally, as Les Miles would say, I personally enjoy taking the integral of e to the x. I find that to be pretty nice also. Huh? Do you know what to do with a to the x, where a is just some number? Do you know what to do with that? Do you know how to take the derivative of that? Have you ever heard of a document called Hardy Notes?
I've heard of the Hardy Boys. Heard of the Hardy Boys.
Well, I'm talking about Ms. Hardy's Calculus 1 notes, those things she gave out in class. Most of you had Ms. Hardy, a few of you had me for Cal 1. But I looked back in Hardy Notes and I found where she taught you guys how to do this and how to take the derivative of this. First, I'd like to talk you into the idea that a to the x is the same thing as e to the x log a. I'm going to need that. So I want to talk you into it. Look at that for a minute and tell me whether you believe me or not. Mr. Executive Producer, do you believe me?
I'm working on it.
You're working on it. Well, let me try to convince you.
Yeah.
The power rule for logarithm says that if you have a power inside the log, you can just pull it out front, right? And the reverse of the power rule says this number in front of the log can go back in the log as an exponent. So I'm going to write this as e to the log of a to the x. But you know, don't you, that is supposed to look to you like 3 times 1/3. Anytime you see e and a log together, do what? It is a inverse function. You know I don't use that C word because that implies that it goes away, and it really doesn't go away. It's expressed as the identity operator, but I've told you more than you need to know. They wipe each other out. They are inverse operators, right? So what's left? Now have I convinced you? Isn't that like a trig identity where you start with two things that I'm telling you are equal and then I have to convince you that they really are? Have I done it? So now what I want you to do is tell me what the derivative with respect to x of a to the x is. Well, that it has to be the derivative with respect to x of e to the x log a. Because I just showed you that the two were equal, right? But how do you take the derivative? How do you take the derivative with respect to x of e to the 2x to the third? How do you take that derivative? You use what? What? You don't have to. You could, though. Chain rule, right? Chain rule? Doesn't the chain rule say take the derivative of that as though it were just x? So that means just copy it, doesn't it? And then multiply it by the derivative of the exponent, huh? I'm going to do that right here. And I'm going to take the derivative of e to the x log a, and that is just e to the x log a times log, times log a. True confession time, y'all. How many of you are wondering where that log A came from? Anybody? Anybody brave enough to admit it? I took the derivative of the exponent. Isn't that the way you take the derivative of a log? And the derivative, log A is a what? Constant, a number, isn't it? A is a number, so the log of it's a number. Think of it as log, natural log of 7. Couldn't you put that in your calculator and get a decimal number? So isn't log A times X just the same as 2X? But now I have, this would be, using what we did before, this is e to the log of a to the x times log a, which is, there's that inverse again, a to the x log a. So somebody tell me in words what that means. What's the derivative of e to the x? E to the x. What's the derivative of a to the x? It is a to the x. But for anything other than base e, you have to multiply by the log of that base. It's just that easy. Every other rule that you know works. Now, I took time to do that because that's Ms. Hardy's business right there, but I'm going to use it. And that is, I feel compelled to ask you, how about the integral of a to the x dx? What's that equal to? And don't tell me you don't know. What's the integral of e to the x? E to the x, huh? So wouldn't you bet from what we just did that it's going to have a to the x in it? And wouldn't you also bet from what we just did that it's probably going to have a log a somewhere? Why? Because you know that taking a derivative is scrambling an egg and integrating is unscrambling an egg, huh? Okay? So, I'm going to use, in order to answer this question, do you remember that section in Cal 1 on antiderivatives? How did you learn to take antiderivatives? How did you learn?
So, Moses,
Yeah,
Moses,
hey,
Moses summer course, they just
Write
kind
'em
of
on my
formula and like plug it in.
yeah, you really are thinking backwards, aren't you? Didn't you say in incorrect grammar, what did I take the derivative of to get this? Isn't that the way, didn't you quickly decide that that's the way you do antiderivative? So, what I want to ask you is this a true statement? I know there's needs to be a plus c there, but I'm going to take c equals 0 just to keep it simple. Is that a true statement? Why? Exactly. Didn't we just get through saying that the derivative of a to the x is a to the x log a? And if that's so, I ought to be able to integrate a to the x log a and get what, Josh? A to the x, thank you. A to the x. Okay? Now, what did you tell me about this log a? The word that Travis used was constant. So like any other constant, can I take that log A and pull it out front of the integral? So now I have, on this side, I have log A times the integral of a to the x dx is equal to a to the x. And if I divide by log A, I get the integral of a to the x dx is equal to a to the x over log A. And now I'll put the c. Pretty slick, isn't it? Didn't we do it the same way you learned how to do it with antiderivatives? Okay, file that one away. All right. Now, your book, you'll notice in your book, they go back through the properties of logarithms in this section. They talk about how to break logarithms up and how to handle multiplying exponents and all of that. I'm not going to do that, but I am going to show you something because you worry me about your about being so tentative in handling logs. And this is going to be a little bit of a log reminder. And that is, what I want to do is, I want to take this. I want to take that and I want to break it up into separate logs. Do you remember how to do it?
The log of 3x times square root of y minus the log of z squared.
Very good, Daniel. Very good. Another gold star for Daniel. Good. I'll guarantee you you've never seen this before. I always say about my friend Ms. Black, who is a fine teacher, that she can't use the gumbo rule because she don't know how to make gumbo. Ms. Black's from New Jersey, and they don't make gumbo. How do you make gumbo? Don't you just cut stuff up and throw it in the pot? And this is where I got the name for my gumbo rule. If you'll just remember my gumbo rule, you'll quit having trouble. The gumbo rule says that if I want to chop a log up into parts, I take everything out of the numerator and add it, just like Daniel did. That's exactly what Daniel was thinking, weren't you? You knew that those two were plus because they were in the numerator, right? And everything that comes out of the denominator, you subtract. Doesn't that make the whole process pretty simple? So, what I'm telling you is, if we multiply or divide inside a log, are we multiplying and dividing inside a log? We can break it into parts. Parts? I break it into parts like that. I see 3 parts. And that rule says that we simply can create 3 separate logs . Has anybody seen any rocket science yet? No. No. Now, I remind you of the power rule. I could have broken it into 4 parts, couldn't I? What would the 4th part have been? The 3 and the x, right? And I started to do that, but I'm going to say that this is log 3 plus log x plus 1/2 log y minus 2 log z. I violated my promise to you from the first day. All I can say is I did it on purpose. It doesn't count as violating a promise if I did it on purpose. And that is, I left a couple of steps out because I want to give you something to think about. Is everybody okay with what I did? Now, doesn't that help you as far as the mystery of logarithms? And when we first started doing integration, did you notice that I like to break a complicated integral up into parts? Have you noticed that? My I1s and I2s. If I get a chance, I'll take a complicated integral and call parts of it I1, I2, and I3, and I'll have 3 easy integrals, and I'll do those, and then I'll put them back together for my answer. Isn't that a very good way of breaking things into parts? All rise. The queen has arrived.
One day I'm gonna be able to sneak in and sneak out ninja-like without me noticing me.
Just your presence. Questions, anybody? Doesn't that help you? Oh, let me ask you this. I always get asked this. Can't use my gumbo root, can you?
You can use it on, split them up to 2 candy.
Isn't any number divided by 1 just that number? So now don't you have a numerator and a denominator? Yes or no? Okay. And the log, natural log of 1 is 0. You remember? Okay. All right, there's my short review. I feel a little guilty taking even that much time.
So what would that be?
What?
The
That?
if you just separate it with the x, or the cube root of x squared, would that be 2/3 ln x?
I see 3 parts, and I'm going to ignore the 1. Feel free to do what I do. Okay? So those 2 come from the top, so isn't that log x plus 2/3? Now I'm not going to skip that step.
Well, I just wanted to answer.
I know you do, but I feel guilty, Josh, when I break my rule. And then I pull that out front. And I didn't bother to write the log 1 because we know that the log for any base, any positive number base of 1 is 0. Okay? Now, tell me about this. What's that? And if anybody tells me that that's 1/x, I'm gonna have the big one. So don't tell me that. Go ahead. All you sharks, tell me. Knowing what you know right now, you can't tell me. Right now, you can't tell me. The best way that you can do it right now is guess what the answer is and keep taking derivatives of it until you find just that. But in chapter 8.1, good old chapter 8, you're gonna be able to tell me what that is. But you gotta have integration by parts to do it. And we're going to get to chapter 8.1, and it'll be on this third test. But for right now, you can't tell me. Okay? Just don't tell me that's 1 over x. Okay?
It's like e to the log of x.
Yeah, log, and then some more. We'll get to it. Here's one. What's that equal to? That's right, minus cosine x. Right? How do you know you got the right answer? Take the derivative of it. That's as big a pain as integrals are. With every interval, you can find out if your answer's right. Before you turn the test in, you can find out whether the interval's right or not. How about this one?
Sine x plus c.
No big deal, huh? How about this one? Explain to me how you could, how come those first two look so easy and this one doesn't?
Sine, cosine.
Very good. Very good. First thing is, let's see, you know that the derivative of the tangent is what?
Secant
squared.
Secant squared. That doesn't really help us, does it? And you know that the derivative of the secant is secant x tangent x, but the problem is you still got a secant x in your way. And my point to you is that you don't know what that is. There's not a convenient answer for tangent x. But yet you're going to have problems where you're going to have to integrate tangent x. And Daniel just told you how. Did you hear him? He said, use the trig identity. This is equal to the integral of sine x over cosine x dx, huh? You said it? Okay, Matt.
Yeah, hey.
Matt.
Think the same thing.
Matt. For our viewing audience, in the subscript, we'll have the names of all of the actors in this drama. What about it? Oh, come on now. First thing is, it's not so easy, right? But we're going to go back to my 6 steps. The 6 steps for what you let u be. When you have an integral that you can't integrate, isn't your first response to try to do a substitution?
You can make cosine or u cosine, I'll get rid of sine.
Exactly. Exactly. One of those 5 steps is what's in the denominator, right? And that's about the only thing you can do, isn't it? So let's try it. So I'm going to say, I'm going to let u be equal to cosine x du is equal to minus sine x dx. Or minus du is equal to sine x dx. Now doesn't my integral become 1 over u du?
Negative.
With the minus out front, huh? Agree? But you do know what 1 over u is, don't you? What's the integral of 1 over u du?
Natural log of
Natural log of u. Which is equal to minus the natural log of cosine x plus c. Agreed?
Yeah. I was just about to say the absolute value.
However, in the back of the book, it says, anybody tell me why?
Negative inverse of this.
Yeah, this negative goes back inside the log, right? Do you agree? So isn't minus log cosine x equal to the log of cosine x to the minus 1 power? Is that right? Which is equal to the log of 1 over cosine x, which is equal to the log of secant x. Okay? You gotta understand logarithms in order to be able to do that. So now you can find an integral for tangent x when you need it. I don't even try to memorize it because I know how to get it, and there's only so much room up there. And the same might be said for your 3x5 card, right? Okay. How do you think the integral of the cotangent would work? How do you think you?
Cosine over.
Yeah, cosine over sine, right? Right? And wouldn't the steps be the same? So I'm not going to do that one. Okay. I'm ready to work some problems. This is example 2 on page 425. I want to take the derivative of that. First thing, don't you notice, is that it's not LN. Agreed? Second thing you notice is there's no base there. Does there have to be a base there?
Just base 10 with some base.
That's right. If you leave the base off, it's called the common log, and it's understood to be a 10, right? So I want to take the derivative of that. But you remember that that is equal to the natural log of 3x plus, oops, that is equal to the, that's equal to what? You tell me. I didn't show you how to, but you know that. I think this is equal to the natural log of 3x plus 1 over the natural log of 10. Do you remember change of base from college algebra? If you don't, here's a quick review. Log A of x is equal to the natural log of x over the natural log of whatever the base was. And that's called change of base. Change of base. Now, once I do that, what's the big deal about changing it to LN? What's the big deal about changing it to LN? What? You know how to take the derivative of LN, don't you? Agree? So this then is, this is equal to 1 over LN 10. That's just a number, right? Everybody agree? Times 1 over 3x plus 1 times 3.
Why didn't you keep the log for the second, like 1 over ln 10, why don't you do 1 over ln 3x plus 1?
I'm taking, once I take the LN 10 out, I have this. You can pull a constant out front when you're taking derivatives, right? Right? But once I get to taking the derivative of the log, don't you remember the way to take the derivative of the log is put what's inside the log on the bottom and the derivative of it on top? So what I did is I took what was inside the log, 3x plus 1, and then I took the derivative of 3x plus 1 and put it on the top. Okay, Spencer?
I see what you did. I'm just
Okay.
clarifying it.
Well, this is a good time to ask.
So is this?
That's as pretty as I can make it. Any of you want to pretty it up, welcome to do it. Yes, sir.
So when it's assumed constant, you're gonna leave the natural log in front of the 10 when you break it
Yeah, the natural log of 10 is just a number. You would hit the LN button on your calculator, put in 10, hit enter, and you'll get a string of decimal digits. It's just a number. So it's treated like a constant. Yes, sir.
So, if you treat it like a constant, then why are you putting the denominator once you take the integral of?
Because it already was in the denominator to begin with.
Okay.
You follow what I'm saying? If you had, if you were taking the derivative of 1/2 x to the third, and you wanted to take the derivative of that, wouldn't you, the 1/2 just come out front because it was in the denominator to begin with? And then you would just take the derivative of x to the third.
But see, you have 10x, it's not over 1 there.
Say what now?
You have ln 10 d over dx, ln to the 3x plus 1 on the top right corner.
Right there?
Yeah.
So if you want to.
Well, why didn't I put it over 1? Daniel, tell them why I didn't put it over 1.
Because you forgot to.
All I can say is you guys will be owed one of these.
Now I
Thank
see-
you.
I already see where it came from.
You don't have to be that nice, though, to point out my mistakes.
Oh, I didn't know it was a mistake.
Oh.
I'm still wondering about all this.
Nor do you have to be brutally honest. You can appear to know when you don't, and it's perfectly all right.
I assumed you were treating them differently. Now
Yeah.
I know where
Now,
I'm good.
and that explains your question, Dad.
Well, no, you did it earlier too.
This is a new strategy in teaching that we use, where we make mistakes on purpose so classes will ask questions. Sorry about that, y'all. Okay. Everybody all right with that? What's the trick? The thing to remember is, unless it's a letter, it's a number. Did I ever tell you, in high school, we had this great big left-handed pitcher, and he was just conveniently wild, which meant that no batter on the opposing team would dig in, right? And he could hum that baseball. He really could. And he got a scholarship to play baseball at Tech. Went to Tech and had a good college career over there. And he came back to see our coach, and the coach said to him, he said, well, how do you like it over there? And he said, Coach said, everything's going great, except those people over there are adding letters instead of numbers. So what I'm telling you is, unless it's a letter inside the log, it's a number, right? And just treat that log with a number in it as you would any other number, okay? This is A and this is B. Any suggestions? In fact, you're going to have to tell me. Do you know how to integrate log base 2? Did I show you that?
That's the same as what you did earlier.
What do you mean?
It's just ln of x
Yeah,
over.
very good. Change your base. The point is, I didn't show you how to integrate log 2 of anything. And there's a reason why I didn't show you. I don't know how to integrate log 2 of something. If I knew, I'd tell you. I just don't know. So what I do is I change it to ln, natural log, which I do know how to integrate. So what I'm going to do is, and this time I'm going to put the step in because you'll help yourself if you do it to keep from getting tangled up in this. This is the integral of log two of x times 1/x dx, which is equal to the integral of the natural log of x over the natural log of 2 times 1/x dx. Have I done any calculus yet? All I did was to change a base. But do you see why moving that x would help you and keep you from getting confused? Now this, we know, is a constant, huh? So I'm going to pull it out front, and I'm going to have 1/log 2 times the integral of log x times 1/x dx. Is that right? But you don't know how to integrate log x, do you? You don't. But you do know how to integrate what's on the board. There's a difference. This one on the board has a 1/x in it, doesn't it? Do what?
1/x integrates to log.
Absolutely. The derivative of log x is 1/x, right? So what if we let u be equal to log x? The whole thing. What's du?
1/x dx.
1/x dx. Pretty slick, isn't it?
So you can't integrate ln x?
I can't. You'll be able to before test 3, because I'm going to put it on test 3. You'll be able to do it, but you can't right now. Okay? But then that is 1/log 2 times the integral of u du. Is that right? And then this is equal to 1/log 2 times u squared over 2 plus c. But that's equal to 1/2log 2 times log x squared plus c. Why did I have to put that parentheses around it? Why?
Because you're squaring the whole.
Exactly. Isn't that back to test 1?
Yeah.
What some of you did on test 1 is, remember the rule is that an exponent goes only with the closest number or letter, and if you want it to do anything else, you have to put it in parentheses. Questions? Anybody? Anybody? How in the world would you know when to let u be equal to log x? The easy answer is whenever you have a 1/x to go with it. Okay? I want to do number 25 on page 426. This is one of the homework problems. I want to work a couple of these. Any suggestions? Why, Travis? Why did you tell me that? Travis just told me to let u be equal 1 plus e to the x. What in the world made you think of that? Yeah, that. First thing is, I told you if you can't integrate it, quote, normally, by conventional means, do a substitution. And of the 5 rules, that's the only one you got, isn't it? The part about letting it be the exponent, if you let it be the exponent, that's letting u be equal to x, and that doesn't change anything, does it? You just rewrite the problem with u in the place of x. So the only rule you got is that. Travis gave me a better answer, and that is it works just like the one we just worked. You're supposed to notice that if you pull that e to the x in the numerator off to the side, you would have the derivative of what's in the denominator. Okay? So, let's do it. And that is, u is equal to 1 plus e to the x, du is equal to e to the x dx, huh? So, there's that, and there's that, and we're right on the verge of living happily ever after. This is 1 over u du. Do you agree?
That making sense.
I'm crushed. I think I'm right. Am I right, Ed?
It
Beth?
should be ln absolute value of u.
That's ln to the ex. So that makes it go away.
Oh, cause that's 0.
Daniel sat on the tag. Oh,
Well, cause the log of 1 and 0 plus log of e to the x, which is just x,
yeah,
plus c.
yeah. Let's see if I'm right. I think this is equal to log u plus c. Do you think that?
Right.
And I think that this is equal to the log of 1 plus e to the x plus c, and I can't do any more now. If the 1 hadn't have been there, we'd have been in business, wouldn't we? I can't do any more than that. Ed?
Yeah, pardon, mostly in order tables we put absolute value.
Yeah.
Do you take off of that, or?
No, I don't.
Okay.
I view it a little bit differently. You know how picky some textbooks are about domain of a problem? And I've always taken the position that I will find out whether it's in the domain or not. If somebody take the natural log of -2.
Gonna give you a number.
Negative?
Yeah, natural log of -2. And that's how you know that it's not in the domain. Do you see what I'm saying? Most of us by now know that you can't take a log of a negative number. It's undefined. But even if you had forgotten that, if you try to put that in the problem, it's gonna blow up on you anyhow. You follow what I'm saying? And that's why, the further I go in calculus, the more sloppy I get about that. Because, the whole context of the problem dictates what you're gonna put in for the variable anyhow.
Okay.
And in a lot of physical, circumstances, you're not gonna have negative time.
I understand they drilled that into us when I took
Yeah.
this thing 40 years ago.
Yeah, yeah. Everybody okay with that? Look at number 34.
But it wouldn't be wrong on the test if we did have one like that, if we just left it as natural log of 1 plus e to the x plus c.
Say what?
It wouldn't, would it still be wrong if we left it as natural log of 1 plus e to the x plus c? Would it still be
1 plus e to the x, what now?
Your answer, you know, how you said that is equal to x plus c.
It's not equal to x plus c.
Yeah, it's not.
Oh, okay.
It's not. It's not.
I'm good with
It's not.
it.
I thought you were asking me, and isn't the great temptation to break that into log 1 plus log of e to the x? Isn't that the great temptation?
That's what I thought you were trying to do. with
Yeah.
it, and put-
No, what I did is I forgot about the 1, Dan.
Oh,
But isn't that the great temptation? But remember, my gumbo rule says if you are multiplying or dividing inside the log, it doesn't say a thing about adding and subtracting.
And see, we'll just believe whatever you put on that board is true, and then try to figure it out later.
Well, figure this one out. I'm going to do the deal I showed you where I take the limits of integration off. I'm going to integrate it and then I'm going to put the limits back on, right? Okay?
We can do the same if we write consider on the test.
You know what consider says? Consider says I'm starting over on a different problem. If you just leave the equal sign off, you're starting over on a different problem. But if you put an equal sign, those two integrals are not equal, are they? And I won't like that. I put consider only because that's a way of saying to the guy that's grading it, I'm not trying to tell you that these two are equal. I'm starting over on something else. And consider sort of means I'm going to come back to the original problem. And do what I do. If you do it, give this a name so you don't have to recopy it. Okay? Help. Any ideas? Substitution. First thing, you can't work it by conventional means. You can't just work it. You gotta do a substitution. What about the rules? Exponent?
And you have to,
You can break it down, it's just constant.
Do what?
You can break it down and make it a constant, and just make, you can just integrate it. Or can you not do that, cause it's.
well, it would be, if you did that, it would be e to the log of, or e to the log of x times the log of 2. If you tried to do that, you'd have a log.
Let's separate them into 2 to the log of x times 1 over x, and then make my exponent my substitution.
Exactly. And it falls right into place. So, what we're gonna do is we're gonna rewrite this as the integral of 2 log x times 1 over x dx. Because I noticed that that 1 over x dx is a derivative of log x, huh? So u is equal to log x, du is equal to 1 over x dx. And now this integral sign, you don't have to draw any arrows. I know what you're telling me, that it's equal to the integrals, to the equal sign above. So now, don't I have the integral of, did I get ahead of myself a little? Of 2 to the u du. But isn't that one that I just got through doing earlier in class that you might want to put on your handy dandy 3x5 card? Isn't this equal to, don't I remember, that this is equal to 2 to the u divided by the natural log of 2 plus c? Does everybody remember where I got it?
I do, but, you know, it seems like that one wouldn't be below either.
Well, let's see, I'm subject to not remembering. What I said is that the integral of any number, like 2 to the x, is equal to 2 to the x divided by the log of whatever that number was.
Well, how did that log get down to the bottom again?
Through this process right here.
Right, but it wouldn't ever go below and stick the, wouldn't you just multiply log A to A over A to the x?
No, it stays there as a log.
But see how you had it on the middle row? It's
Right here?
Yeah.
Yeah, but what I was doing, William, is I just got through showing that if I take the derivative of a to the x, I get this.
Okay.
So I just started with that and said that because of the way we do antiderivatives, this had to be equal to a to the x. And the way it got in the denominator is I pulled it out front and then I divided both sides by it. What I would suggest you do is you put this on your card. Or here's another one. Here's the way I remember it. The way I remember it is the integral of e to the x is e to the x, right? So the integral of a to the x is a to the x. But because it wasn't e, I have to take the log of the base and I divide by it. Now, this is equal to, then, 2 to the log x over log 2 plus c. Is that right? Kenny Rogers? Kenny Rogers? Know when to hold them and know when to fold them. Nothing else you can do. Quit. Now, I got to go back though. I got to go back now. You remember I, don't you? I is hidden from us now. I is equal to 2 to the log x over log 2 from 1 to 2. Everybody follow what I'm doing? Wouldn't that have been a mess to change the limits of integration and all of that? So what I'm doing is now I'm going back and putting it in. So I think this is equal to 2 log 2 to the log 2 power over log 2 minus 2 to the natural log of 1 power over log 2. What did I tell you the natural log of 1 always is? That's always 0. And what's 2 to the 0 power?
1.
1. So all of that's just 1, right? So at some point, I'm going to take my own advice and quit. And this is that point. Yes, you could write it together as one fraction. My question to you would be, how would you know whether that will help you or hurt you by putting it together? The answer is you don't. Can you think of anything else to do? I'm fresh out of ideas.
Miles, on the caution, the homework gets very specific on how you have to end something like that.
Yeah.
Don't get frustrated.
Or if you do get frustrated, get over it fast. Because the next problem is going to frustrate you again. Okay? Everybody okay with that? All right? I've got one more. Here is a butte. This one is a honey right here. This is number 23. The problem in the book has V's in the place of X's. Sometimes my V's and my U's get to looking too much alike, so when I copied it, I changed the variable to X. First, does everybody agree that we're going to have to do a change of variable because that's the only thing we know how to do right now? And what's there isn't going to work by any stretch of the imagination. Agreed?
You make, that's not what work.
Exactly. Isn't it really? Remember, if you'll just use the thought discipline, just use thought discipline, and don't get rattled by all that trash that's in there. And that is, think of my 5 steps. Look for one of them. And the only one you have, again, it can't be the exponent, because if you did that, you'd say u is equal to x, and that doesn't help you any, right? So the only thing left is the angle. So let's do it. This is another consider, isn't it? I'm going to call this I, and this time and just say now. Now, or consider, or just write it with no equal sign, and I'll know you're telling me I'm starting over on another problem. Ed?
The answer's gonna be one.
Dr. Thomas predicts the answer is 1.
But don't just write that on the test, you won't get any points.
That's correct. Don't do that. All right. U's going to have to be e to the x, and du is going to have to be e to the x dx. How nice, huh? So doesn't that change our integral to 2 times the integral of cosine u du? Everybody agree? But you can integrate cosine, that's 2 sine u plus c. Agreed? Which is equal to 2 sine e to the x plus c. And now I go back and I say I is equal to 2 sine e to the x from the log pi over 2 to the log of pi over 6. Which is equal to 2 times the sine of e to the log pi over 2 minus the sine of e to the log pi over 6. Agreed? But what are you supposed to think when you see those e's and logs together? Inverse. Those go away. So now don't I have 2 sine of pi over 2 minus the sine of pi over 6, which is equal to 2 times 1 minus 1/2, which is 1. Ed, you were right.
I can do that better in my head than I can do Math 97 arithmetic.
You know about me and arithmetic. Questions? Anybody? Didn't that look like an awful problem? And now doesn't it look easy? The question is, will it look easy on March, what is it, the 3rd? That's the question, isn't it?
Miles, remember that movie Back to School?
Yeah.
It was the economic professor was torturing Rodney Dangerfield. It says, part 3 of subsection 6, so the answer is 3. Damn it, he got it.
Yes. Yes. This summer chapter 8's going to look like that, Ed. Does this help a little bit with handling transcendental functions? Honestly, I thought seriously about just skipping this section because you'd already seen all of it, but I think it gives you a little bit of a review and